The world is new to us every morning. This is God's gift, and every human being should believe as a rebirth each day. A blissful day to all the participants attending this webinar. I, Bindu Norona, Assistant Professor, Department of Chemistry, will be the MC for the day. It gives me an immense pleasure to welcome you all to the second day of the international webinar on trends in chemical science, challenges and opportunities. I request you all to stay connected, making use of stable internet connection throughout the webinar for all the valuable inputs given by the eminent speakers. Participants will be provided with an opportunity to interact with the speaker towards the end of the session. Questions along with the name of the participants can be posted in the chat box, which would be discussed at the end of the session by the speaker. Please note, it is mandatory to all the participants to fill the feedback form for each session to procure your e-certificates, which will be sent in the chat box at the end of the session. Nothing can be more certain than this, that we are just beginning to learn something of the wonders of the world to live, move, and have a being, says William Ramsay. It is our privilege to have today's speaker for the first session, Dr. Sachin Ramachowdhury, scientist and assistant professor, Department of...
It's my pleasure to introduce today's speaker, Dr. Sachin Ramachowdhury. Dr. Sachin Chowdhury is currently working as scientist in magnetic resonance in the Department of Spice and Flavor Science at CSIR, CFTRI Mysore, and also as assistant professor in ACSIR. Dr. Sachin plays a central role in directing the CFTRI's NMR facilities and has an extensive network of contacts and collaborations within CFTRI, UK, US, IIT Bhilai, and also IISc Bangalore. In 2017, Dr. Sachin was awarded a very prestigious Marie Curie Fellow by European Grant Horizon. In addition, he was also awarded with the CBMR NMRS Gold Medal Award for excellence in research in the field of NMR spectroscopy. He has worked as a postdoctoral fellow at the High-Field NMR Center of Lyon, France. He has developed a large number of important new methods in solutions and solid-state NMR and related techniques. His outstanding research publications to date resulted in 36 peer-reviewed publications. His H-index is 17 and with I-10 index 25. With this brief introduction, I welcome you, sir. The session, you can take over the session. Thank you. Over to you, sir.
Sachin, sir, can you please unmute your mic? Hello, sir.
Yeah, now I'm audible.
Thank you, sir.
So very good morning to everyone, and first I would like to thank for organizing. Okay, I can start now. So first I would like to thank organizer for giving me an opportunity to speak over this and international webinar on current trends in the chemistry. Earlier, I thought to talk something on like a very basics of NMR and something like that. Then later, I realized that your title something sounds like something trained in chemical science. So I thought, why couldn't I touch something on very trained method which I have worked in my postdoctoral study. So today I will introduce that technique for you guys. And if you want something on more relevant on NMR, we can take some workshop as I'm in Mysore itself. Okay. So today's technique will be something like it's basically NMR, but something like hard advanced in NMR. So what do you call it? Basically, solid state dynamic nuclear polarization enhanced NMR. So we're going to see like how it is different from the conventional NMR. Okay. So this is what exactly I do any in CFTR in Mysore. So basically, our lab is dedicated to the food science and technology. So and especially our department working on the spices and flavor science and plant texture products. What my our group does it here actually, we'll try to look at the quantification of secondary metabolites, structure, dynamics, metabolism, and we try to understand the geographic origin by using NMR as a tool actually. So NMR will be applied to understand the food processing and the food safety adulteration issue in that way. So today I'm not going to talk about this one and just give the brief idea that what I'm doing in CFTR. So starting with a session on the solid state dynamic nuclear polarization enhanced NMR. Okay, so like what do you think about when you ask about you something? What do you think that NMR can do for you? So if I ask simple basic questions to let's say postgraduate student or many chemists, they will say that let's say I make some molecule something like I synthesize some molecule like A to B or B to C or something like let's say as a food chemist we extract some secondary metabolites and we want to know that whether our synthesized molecule is the same what is synthesized or is it some different. So NMR allows us to figure out that what we are talking making it. So let's say I'm making something curcumin or I'm extracting something curcumin or I'm doing any chemical synthesis to try to understand what my synthesis has done, whether I'm right or not. We do that in NMR technique. So this NMR is one of the principal techniques along with the mass spectroscopy. So apart from that, like many times we just think about NMR only do the structure confirmation, but this is not a true. This is only 10% true. NMR has done a lot of things for us. Something like you can understand the conformation, for example, local structure. If you want to see the interatomic distance, you can say the geometry of the molecule like cis and trans, protein structure, carbohydrate, and many important and complex biological samples. You can do the even crystallography if you want to understand the that if you want to try to understand the three-dimensional structure. If I ask you, will tell X-ray crystallography. But nowadays, the NMR also has a significant contribution to understand the three-dimensional structure of the like proteins, or you can say small molecules or drugs, something like that. Okay, in polymorphism or something like that. Even we can see the many other NMR not only restricted to the organic molecules, but it can apply to any disordered solids like zeolites, polymer, glasses, liquid crystal, and we can understand their like domain size, phase separation, and many more like that. And furthermore, like the molecule sometimes has a very interesting property. They will go from one state to the another state. They what we call dynamic. So they have different structures actually in the same solution state. That structure also can be understand by using the NMR. So we can see their diffusion, their rotations, or you can see their different interaction. Something. So NMR will do many things it can offer. So that is what like if you see that. NMR is one of the complex technique. It's just not by using by chemist, but it has a see it's a very complex thing. It needs a knowledge in a various technique like mathematics, physics, chemistry, and medicine. So the NMR is basically the very interdisciplinary tool, and that can you understand by this not only one Nobel Prize. You can see compared to any other techniques, Nobel Prizes in NMR has almost like a 4 Nobel Prize, starting from the physics, first Nobel Prize in physics for NMR. It just for giving the quantum mechanical description. It's just not like a chemist. Only that how the quantum mechanics works for that one. They got the first Nobel Prize. And later in 1991, Richard Ernst has proposed that NMR can be utilized to understand the basically like chemistry, like structure of the molecule. Like how can I say ethanol or not, something like that. So in that way, it has applied. So that got a second Nobel Prize. But things never stop, and if you things move more on challenging things like protein structure, three-dimensional structure. That earlier is known that only XRD can be done, but now the MR also has that contribution in that one. And the third Nobel Prize is for the development of NMR method for 3D structure basically to determine the protein structure. Okay, so this is about all about the basic science functions. Not only NMR is restricted to basic science, but it applied to our daily routine technique, what they call a MRI. Like nowadays, MRI is one of the diagnostic tool for daily analysis. So that also can be done what you call magnetic resonance imaging. So you can see that NMR also ranging from one dimension to the higher dimension, where you can see the protein structure. Up to that, we can see the how MRI can help in diagnosis. So it has a range of application, So that is what the NMR is like true measure of multidisciplinary tools in science. So moving something on problems. So basically now comes to the problem. So if you see that what is the problem with the routine NMR technique actually, and you see the when you want to do NMR, you can see that on the left side I have shown that NMR spectrum and the IR spectrum. You see what you observe is that in NMR spectrum you get lines. You get lines. Very nicely lines, very narrow lines. But if you say something about IRs, you can see this is very broad. Okay. Now what I'm going to talk about the sensitivity. NMR has a problem sensitivity. So what is sensitivity? Okay. Sensitivity has a two definition. It has a two facets. Okay. One can be that in terms of structural arrangement. Okay. This was a simple example I took. Molecule is curcumin molecule. Okay. If you see the curcumin spectrum, actually, gives some lines. So now it is a very narrow line. So if you see the same, if you do the IR for the same thing, you can see that IR is a very broad spectrum. There are multiple lines and broadness. So what in the case, the NMR is very sensitive even for small fluctuation in the structure. So that is it indicates. The broadening is very minimal compared to IR, or you can take any technique like UV or something like like Raman spectroscopy. They are very broad in nature. So in that case, the sensitivity is not so like high sensitive. But NMR is a very narrow line, so you can see that even small fluctuation can be monitored with NMR. But sensitivity, it has another issue also. I told about the structure, but sensitivity you can talk in terms of concentration. So when you are going for analysis for NMR, like what is the problem? They'll ask you to give something like a more amount of sample. Sorry, a more amount of sample. So for example, if you want to do HPLC or GC technique, you require in nanomolar or picomolar concentration. But when you're submitting sample for NMR, you require something around like in millimolar concentration. So in that way, NMR is what you call insensitive. You understand? I define here in this slides the two facets. One is the sensitivity in terms of structural element. In that case, NMR is a very sensitive technique. Okay. However, if you compare the sensitivity in terms of concentration, NMR is a very insensitive technique. So we required large amount of sample for NMR analysis compared to the other technique like mass, IR, or something like UV or something. So that way. So now what happens? So why that sensitivity has a problem in NMR? Now, if you see the quantum mechanical description of the NMR, let's say these are the spins. There's arrow indicate one-headed arrow indicate the spins. They indicate when we don't apply magnetic field, they are in a degenerate state. Okay, but when you apply the magnetic field, So they will get separated according to human interactions. Okay. Now the separation. Now you see the separation. This is the separation, and that resonance condition is given by V is equal to this one. Okay. Interaction static magnetic field. This one actually is given by this one. So what happens? I'll explain the further actually. So if you see here, the see here, so the number of lines in the ground set are the responsible for getting the higher signal. If the lines at ground set, for example, in this case, plus 1/2 more, you get a higher intensity signal. So you require less amount. But in case of NMR, what happens? The lines are the difference between these two are very small. So there is the lines are very number of lines are very I can say very less. So the intensity of signal is very it's very less in NMR. And the sensitivity of the NMR also depend upon the natural abundance. So the natural abundance, the chiromatic ratio is another change actually. It's just by natural it's there in any nuclei. You can see, for example, proton. It is something around 99%. But if you same thing, if you take it for a let's say carbon 13, it is only 1.1%. So what is indicate that for that one, if I record the proton NMR, I'll get strongest signal. Okay. And if you do the carbon, what happens? The abundance is very less. I require more time. Okay, so you can see this from the right side where I have shown the experimental timing. Okay, for experimental timing, for if you want to record, for example, ethanol, if you want to record proton NMR, it took only 2 minutes. But if you want to record the carbon 13 NMR of same samples, it required almost around 1 hour. So you understood the difference actually. You can see that for proton it just take 2 minutes, but for carbon it's take like 1 hour. So that is what. If you go for any other challenging nuclei like which has a very lower abundance like N15, N15 or any other nucleus like exotic like sulfur or something other nucleus. In that case, the sensitivity will go down again. So for lower abundance nucleus, it takes time. So that is a big problem in NMR actually, unlike in other technique. So how to solve this problem actually? Okay. So the ability of the NMR to get a higher signal depend upon the three factors. One is the natural abundance. I already explained. Okay, the NMR active isotope is okay. It should be abundance is 100% means you get signal immediately. You get signal in reasonable amount of time, like in proton, for example, 2 minutes. Okay, and for if its abundance is very less, it will take larger time. For example, carbon 13 actually. So that is the problem actually. Okay, now the another parameter for sensitivity is the gyromagnetic ratio. That is also affect the sensitivity. And another important parameter is the quadrupolar relaxation. Okay, so basically that I'm not going to discuss more. We need a very technical issue for that. And so for at the moment, natural abundance is a very important parameter, and the gyromagnetic ratio, the two important parameter that affects your sensitivity of the NMR signal. Okay. Now, how to as we know that these are the intrinsic property of the nucleus that can be changed actually. So, like how to change the sensitivity now? Okay. Now, what is so there can be one option. We can go increase magnetic field. From let's say, like example, you are doing on 80 megahertz, so you can go to 1.2 gigahertz. So you can increase the magnetic field. So what happens if you increase the magnetic field? The distance between the alpha spin state and the beta spin state is increases. So with the increasing the distance between these two energy states, the more number of spins will go to ground state. More number of nucleus in the ground state, you will get higher signal. That is there. So that is the benefits. But what happens every time to getting higher and higher magnetic field is also a problem for the cost. Cost also will increase, the maintenance will increase. So every lab cannot be have it that one. So sometimes it's very challenging to go very high magnetic field. So that is one of the big disadvantage in that way. So there's another way like uh, another way, how do we increase the nuclear polarization actually? So how we can increase that actually? This is one of the three cases I have shown it actually. You can try to understand. So upper case is like when you apply the magnetic field, the spins are in sorry, when there's no magnetic field, the spins are in a degenerate state. When you apply the magnetic field, there goes the ground and excited state, and that a matching of the energy of the nuclear energy level, so you get some signal. Okay, now what happens? Let's say example, there are three cases are there. Now alpha and beta are the ground state. Okay, alpha is ground state and beta is the excited state. Now you can see that the lines, so two lines. Okay, if you say the extreme left, case one, there are only two lines. Okay, if you see the signal, how we get signal if you do NMR, only this much signal. Now if I increase the lines, for example, in case two, the lines will increase means you get higher signal. Again, if you increase the more lines means you get higher signal. So this is what now what is this is it's increasing the signal to noise ratio and increasing your signal in a less available time. So you can get NMR spectrum very speedily. Okay, so this is what we are to increase the nuclear. How do we going to do it actually? Where to find the nuclear polarization? If you see that what's Boltzmann equation tells that at room temperature, if you work out on this empirical, this is mathematical relations, and if you let's say put for example all the things, for example 290 Kelvin, the upper layer lower energy spin state are almost equally are there, and so there's a little excess of population. And if you calculate the population difference, which is responsible for your signal intensity, is a very small actually. Okay, it's very small actually. So it's very difficult. In that case, NMR is a very insensitive technique. So what happens if you want to submit a sample for NMR analysis? So you require around 2 to 5 milligram compound for H1 NMR, and if you want submitting for any lower abundance nucleic or like for example carbon 13, it requires higher amount of sample. So this is what that impacts on your something like that. Okay. If you same sample, if you want to give for other analysis like HRMS, DCHPLC, it is required in a micromolar to nanomolar range for response. So in that case, the challenge thing is NMR is a very insensitive compared to other. So now how to increase the sensitivity? Now we are going to see that what are the approach can be defined here. So now this is about the molecules. But what happens when you want to study something molecule like a surfaces, something like zeolites, beta organic frameworks, or any nanoparticles, or let's say any nanoparticles. So what happens, the amount of sample present in that one, what happens? It's very less actually. We can understand this by one of the, I understand this by one of the example here I shown it at. You can see that the gray color box is just catalysis, like silica support. Now I put their catalysis, the catalysis, which is my interest of sample or any nanoparticle on that one. So my sample is only 10% or 20%. My rest part is only on silica, which is I'm not interested. So what happens? Again, these are very challenging sample. So your sample catalyst amount is very less here. So what happens? NMR gets very challenging in such a case. In such a cases, actually, for example, zeolite. So this is one of the NMR spectrum, phosphorus NMR spectrum. So almost around 10,000 scan is required for that to get that signal. You can see that still there is a very lot of noise is there. So that is the problem actually. So in that case, to understand NMR of zeolites or any surface material like nanoparticles, it's very challenging because of sensitivity issue. Okay, so that is one of the disadvantage of this NMR. So three key challenges facing NMR if you want to do on the catalysis, something like that. This is a very clear picture that what I was explaining earlier slide. The red and white dot indicates the silica support material, and the blue the dot is my catalysis. So I want to study the catalysis structure. So it's a very small amount, that is what very difficult to challenge. So the problem with the NMR is the sensitivity. I'm not getting anything. Okay, even we can do. So what happens sometimes, like when you're doing NMR is only one day is not one day is not enough to do. Sometimes to understand the structure, you need to do something like a three-dimensional 2D experiment. So in that case, you require higher concentration. So that is what your samples get, NMR get more and more challenging in such a cases. So NMR has a lot of problem in such a kind of sample. Further addition, if you go for like say organic solids like pharmaceuticals, at least they have higher concentration. If I do the measurable silica material, you are decreasing their surface volume, so you're reducing that amount of sample by doing measurable material. Or if you go for nanoparticle, again your sample of interest is going to decrease as the surface area decreases. So if I going from the microcrystalline to nano to other particles, the size is decreasing of the this one. So in that case, the amount of sample of interest is very challenging to determine. So NMR is a very difficult to do to determine such a thing. So how do you can do this NMR of this challenging sample? So so sensitivity is the most important parameter. You cannot do anything. So the basically problem with that one, NMR is a very sensitive technique. So till now I explained that how the NMR has a suffering challenge to get the signals on the materials like nanoparticles or something like that, or you have very low abundance nuclei. In that case, what happens? Where we can find this polarization actually. Okay, so what happens actually? This is where we find polarization. Okay, so what happens if you see the polarization? The unpaired electron is a very good source of polarization. So unpaired electron is basically is electron actually. So you can see that the unpaired electron has a 660 times higher polarization than nucleus. Okay, so that polarization is there. Now the question is that can I transfer this polarization from electron to the NMR active nuclei? Okay. Uh, so that is the question. Can you transfer that? If you do able to transfer it, so you are win. You will get higher signal. You get higher number of lines in the ground state. So you will get signals very fast. And so that is the what to call it. What you call it actually the dynamic nuclear polarization. So transferring electron polarization, it can be any stable radical. Like I say, I have shown here nitroxide radicals to the NMR active nuclei. That is called dynamic. So that is there. You can transfer it and you can get it higher signal. Okay. So this is the, if you compare now, let's say now we are try to understand that if you take the polarization with the magnetic field at different temperature, you can see that at 100 Kelvin, if you see that electron has a 4% of electron polarization, and if you see the same at the same magnetic field at the same temperature, the nucleus, for example, the proton, it has a 0.06% polarization. You can see that there's a large difference in polarization. So that is what ESR is a very sensitive technique. Sorry, sensitive technique in terms of concentration, but NMR is very insensitive in terms of concentration. So now, so this is what basically the history of the DNP, the growth of a DNP. I can say that earlier it was just like theories postulated some small effect, but now recently you can see that a lot more has been done, and the DNP is now is in our day-to-day life actually. Okay, so what is that? This is the what things. So increasing polarization by magnetic field, you can get this one. Okay, so you can increase the polarization of any NMR active nuclei by transferring from electron, and that is what we're going to do the from this one. Okay, now how does this NMR is different from the DNP? Now, if you see the now this is basically electronic energy levels and the nuclear energy level. When I apply the magnetic field, they will split into the ground state and excited state. Okay. Now what happens? They are in a different. Now this is my right side is my nucleus, left side is my electron. Like you will see that there is the energy when I apply magnetic field. So they are in a ground state and excited state. Okay. Now what assume that this is a hypothetical model. There is no interactions now. Okay. Okay, and there are several mechanisms that possible mechanism there in which the polarization from electron it will transfer to the nucleus actually. So today I will show one of the example of solid effect actually. So now what happens once you introduce now dipolar interaction between the proton NMR active nuclei and between the electron. So that is the interaction. When dipole coupling between the electron and nucleus get connected, but now they're connected. Now you can see that they are connected by the hypercurrent interactions. Now what happens now if I put something like if I saturate this transition now, if I use now the if I selectively saturate this transition, this the green one which I shown arrow by what happens if you saturate, what happens? So saturation in the sense I am making their population same. Okay, if I saturate between this, so what happens? So it will go saturation. And so what happens? There will be transfer of population between the electron and the nucleus. Okay. Now, if you see that after saturation with microwave, if you see the population of the nucleus now it is increased now. Okay. Earlier, where what you can see that uh, earlier you can see that there's only two actually. Now we can see that in if after saturation, the red balloons in this direction is more now. Earlier two, now it's a four. So that now it's increasing. That is what we are going to do in DNP. Okay. Now this is one of the hypothetical model. Okay. So this is something like, let's say we have one simple molecule, let's say what for example phenol or something like that. Something. Now this is pink. Pink one is indicates it's basically signal of the DNP. Okay, NMR. If I do NMR of this one, I'll get small signal. Okay, okay, that is signal actually. Now what I do it, I'll introduce the electron that I told you that we need an organic stable radical. I'll introduce that one in a sample. Okay, and once I introduce, so forget about this quenching. Now what I do it actually, I will into the radical and then now as I know that we know that for electrons to saturate their electron transitions we need a microwave. Sorry, we need a microwaves. Yes, microwaves. Now I put microwaves on. So once I put microwaves, what happens? So that will be so electron will transfer its polarization to the NMR active nuclei like proton or carbon or any active nuclei. Okay, so that requires some media like something like a propan, some solvent, something to transfer just to get past over this. So once you do that one and then you do the NMR, you can see that you'll get large signal. You can see that now you'll get a signal like this green signal. So earlier you see that when you do conventional NMR, then you get small signal, but when I introduce something, you get large signal. When you transfer a polarization from electron to the proton, you get a large amount of signal. So that is what called DNP. Okay. So and this is what one of the example of the proline, one of the amino acids. Okay. If you see the upper cases with the DNP, lower cases without DNP, you can see that the microwave on spectra is with the DNP, the microwave operates without DNP. You can see that when I do the DNP, you can get large amount of signal. Here you can see that their signal is in a noise level, right? But here you get some same higher amount of signal. So by doing this one, you can increase your sensitivity. So you can increase your sensitivity, and due to increasing sensitivity, the time will be decreased. Let's say, for example, if I have to do some samples for in 1 hour, I can do it in a like 5 minutes or 10 minutes. So I reduce so much time so that I can save the money or something like that, information time. So how is different from DNP is different from NMR. On the left side here, you can see that this is the NMR, conventional NMR spectrometer. But if you see that DNP look different. Along with the DNP, this is the NMR only. Here we have extra things. You can see that actually we call gyrotron. This is the source of microwave, just microwave source actually. This is how the NMR is different from DNP. Okay. Now, if you see that this is the cartoon representation of the DNP, your sample is definitely in NMR spectrum, NMR magnet here. Okay. Now you pass this microwave goes from this microwave guideline, and it goes to the NMR spectrometer here at the bottom. Okay, where your sample will sit down there. So there will sample go, and you will getting directly microwave, and you can do the NMR. Then you get more sensitivity. So now basically in NMR you don't put a radical, but in DNP along with your sample you need to have stable radical. It can be organic molecule or something. So how to introduce that radical in your NMR sample? That's a very important parameter in NMR. Okay, so what we do it actually, you prepare some take some, for example, 20 milligram of compound, and you put a radical solution of 10 microliter, mix them together very nicely, and then you do followed by NMR actually. Okay, this is one of the procedures I'm going to show you. You can see that the white powder is basically your sample of interest which you want to do NMR. Now I'm putting the NMR. I'm putting the solution of electron. Okay, electron source. Basically, what we call polarizing solution. So I mix with that one the compound of interest. Okay, homogeneously, so that electron source should be covered by each and every part of sample, so that you will have the uniform distribution of the polarization. Now you pack them in a rotor for analysis. So we can do many kind of samples like nanoport, mesoporous, microporous materials, cement or nanoparticle, or you can do pharmaceuticals also. Okay, so you can use the range of sample depend upon the suitability of sample of interest and so sample solvent. Sorry, we can use water. You can use a we can use a TC solvent or DMS or something different. Okay, once you know that, now we can do which many applications. The things which is not possible earlier, that is allow to do now, to do the challenging things like something like basically pharmaceutical, zeolites, nanoparticle, and many other interesting materials, which is very difficult. Or for example, exotic nuclei, something like aluminium, other tin, silicon, something, or many interesting like nuclei, which has a very low natural abundance and gyrometric accumulation. Okay, so this is one of the example of the mesoporous silicon material. Here in this case, I have shown here. In this case, I have shown this is here the silicon materials actually. Okay, if you see the NMR of this one, conventional NMR without DNP, the blue color spectra without DNP, you can see there's no signal, not at any signal, only noise level. But when you put the solution polarizing agent and you do NMR, you can see that you get plenty of signals over here. You can see that many signals are coming. You can see that is possible to see that all signal, and see that how much time you save that. Without DNP, it may require 21 days. So 20, we are saving the 21 days time. If you want to get signal like a red one here, it almost takes something around 21 days. So without DNP, if you do DNP, we can get half an hour something. So this is what the benefits of the DNP over the conventional NMR things, to understand the structure of the challenging samples and a very insensitive samples. Okay, so that you can do many other things like you can do the different kind of nanoparticles like silicon, titanium, aluminum surfaces, silica material, or something like that. Okay, we just put a polarizing solutions. They will polarize your NMR active nuclei, and we can do that one, and you can get a sample of study of your interest or other things. Okay, this is one of the example of the titanium nanoparticle, where they have shown from this group, they have shown that titanium NMR to understand the core structure of the ligand capitals. You can see that the black is there's a no signal. But when you do the microwave on, you do DNP, you get good signal. You can see that you can get some idea about this. Similarly, this is another example of aluminium. Things are not only limited, you can do the zeolites as well. So another example I have shown here, the zeolites. You can see the zeolite structure. This is metal organic framework actually. This is amino functionalized metal organic framework. You can see that the blue version is without there is conventional DNP. When synthesizing this metal organic framework, you have to understand the structure, how they orient and all these things. Then you have to do NMR. You can see that with the DNP, you can get all signals actually. So this is what DNP gets more and more interesting, and you can do that many interesting applications, which is where are difficult by conventional. Okay, another interesting example of on the DNP on the flat surface. Like this is one of the example actually. Here we try to understand the the polymer geometry of the molecule actually. These are the polymers. Basically, these are semiconducting polymer, and when you want to understand their structure, how they oriented when you make them semiconductor, whether they have pi interaction or something like that. To understand the pi interaction, the NMR is a very excellent tool for that one. So you can understand that kind of pi interactions actually, and you can see that within DNP we can see the carbon 13 signal here, and we can do some 2D NMR as well actually. And if you same information, if you want to extract by using conventional NMR, it may take almost 100 days actually. You can see that how much there's substantial amount of time saving with the help of NMR. So these are the other things we able to establish this kind of pattern. This kind of pattern present in that polymer what we propose here. So this is what NMR DNP allows us to see the pi geometry in a very challenging things. Okay, that is not only problem. We can do the many interesting application. One of the example I have shown is something like here, pharmaceuticals. Basically, you can see that you want to see the domain size or polymorphism interactions. Indeed, that can be also explored by using the NMR. You can see that like when you're doing the pharmaceutical any drugs interactions, to assign them what you call the carbon-carbon correlation experiment is very important. Without that experiment, difficult to identify the number of difficult to identify chemical shift. And when you're doing the NMR crystallography, the exact chemical shift and assignment is very important. So this doing this kind of experiment, 2D experiment at natural abundance is very challenging. But DNP allows us to see this, such a correlation within a permissible time, and gives us the very exact assignment something. So that helps us to understand the structure, the polymorphism. Not only the polymorphism, you can you can do the many like a domain size basically, which is important in that kind of things actually. And another application you can see that this dynamic basically, sometimes in some pharmaceutical molecules the size is rotating, molecules are rotating. The dynamics also will can be understood by using the DNP actually. And so this is another example actually where they have shown the interaction of the active pharmaceutical ingredient and the drugs actually. Okay, you can see that you get better enhancement, which is not possible here. You can see that there is small signal here, almost in the noise level. But if you see the red one, you can get good signal. They are enhanced very nicely. You can see that then that interaction can be utilized to understand that. So this is what helpful to understand the structure of the many things. Like for example, here we can and they have done here proton and nitrogen head core experiment, which is basically to understand the space in the interaction between the space, and this kind of interaction was not possible without DNP. So DNP in short allows the very challenging materials and many interesting applications which is not possible with the conventional. So with that, I would like to thank my team, presently in CFTERA and my past members. And I would like to thank you for organizers giving my opportunity to present today to something new. And I hope you have plenty of questions. Thank you. Hello. 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 Hello, ma'am.
Hello.
Yes, I'm done with my presentation.
Thank you very much, sir, for your enlightening talk. I now request Dr. Asha MS to take over the question and answer sessions.
Good morning to everyone. Good morning, sir. So we have got few questions from the participants.
Okay, tell me.
Yeah. The first question posted, like, why double irradiation is also called spin decoupling?
Double irradiation.
Is it audible, sir? Hello.
No, we was breaking. Oh yeah, tell me, man. Yeah.
Why double irradiation is also called spin decoupling?
Double irradiation. What do you mean double irradiation? You're asking. I'm not getting that question. What's been decoupling?
Okay, sir.
No, I'm
Next
not getting it. Go ahead.
Yeah. Next question. How gyromagnetic ratio affects the sensitivity of NMR signal?
Oh, actually, if you see the condition for this polarization, the polarization is difference directly proportional to the kinematic ratio. Actually,
Oh.
so this is I shown in the first slide somewhere in mathematical equation. So that is why the sensitivity depend upon the kinematic ratio. That is the interesting property. By default, nature has that one in every nucleus, like proton, carbons. So next one.
So the request from one of the participants.
Hello. 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 I'm audible. Okay. There's another some questions. I will take it now. I can read it actually. Somebody asked me that can polarizing agents be removed from the samples? When you are preparing DNP samples, when you add that electron source along with some solvents, it's difficult to remove that one. That will go sample will go with contamination, and removing the electron source is challenging. Next question. Uh, why is carbon tetrachloride is not used in NMR? Okay, Shahid has asked this question. So when you into the solution NMR, you use basically. So why we need to use deuterated solvent? Uh, solvent actually what the we know like for NMR we need a very homogeneous magnetic field. Okay, so for example, what happens to the if you don't have homogeneous magnetic field, as I told that NMR is a very sensitive in terms of structural difference. Okay, not only structural difference, any outside disturbance, for example electronic disturbance, or like let's say for example our magnet is NMR magnet is there, and near that some this magnetic field basically it will disturb by the any obstacle. For example, let's say the truck is going from your NMR spectrum, so that will disturb. So that will disturb your magnetic field. Okay. And what happens? And another option, another thing is that the magnetic field is every day it is drift with some magnetic with in some hertz. Okay, the magnetic field will move from some point to some other point. So there will always drift. Actually, it is never stable. So to keep the stable magnetic field, when you are doing any experiment, you have to do. You have to lock, you have to do something referencing. So what do you do? You will freeze that magnetic field for some time by using the deuterated solvent. For example, deuterium, we can lock it for some time so that there is no fluctuation, there's no drift in magnetic field, and you have get a nice signal. So that is the this is important things. And another important point is that, let's say for example, I'm doing the chloroform. I'm using, let's say for acetone, I'm using solvent. Now, why I need to use the deuterated acetone solvent? What is the problem there? Actually, my compound is a 5 milligram. Okay, how do I prepare my NMR sample? NMR sample in type of solution, my compound is 5 milligram, but I have solvent around 500 microliter. So the ratio of the solvent to the sample, it's almost like a 1:1:to 99%. So what if you do NMR? What happens? Your 1% signal will come like small, and the huge solvent signal will come. So they will get, or the solvent signal is too much compared to your sample signal. So to avoid that huge difference between the solvent and the sample of interest, you use the deuterated solvents. That is question. Another I will take going on reading. Okay, somebody asked, please suggest any suitable softwares to improve the NMR FID. So FID is basically the free induction decay that has to be done improve only while doing the your NMR experiment. Okay, if your magnetic field around the sample is homogeneous, then you get good FIDs. That cannot be rectified by software. Actually, you can remove the noise, but not this. Now somebody asked me, okay. Uh, that's all actually. Why? Another question is that why carbon 12 in NMR is not active? If you see that there's some typical formula actually there. They should have odd number of spin, then only they can do it. So there is a typical formula. If you have odd number of protons, odd number of nucleus proton, then only they can give it actually. Every nuclei cannot be given the if you spin I equal to 0, they will not give the NMR signal. For carbon 12, in that case, that I value is 0, so you cannot get the signals. Any more questions? You can put it here. I will answer it. Yeah, I'm done with question, ma'am. Yeah.
Okay. Thank you, sir. Sir, thank you for interacting to the posted questions of the participants.
Thank you, Dr. Asha. I now request Dr. Shaila to give an overview of the session.
I'm glad to conclude the talk given by Dr. Sachin on solid state dynamic nuclear polarization enhanced NMR. Dr. Sachin highlighted on applications of NMR from basic science to the advanced methodologies for the 3D structure determinations. He spoke on sensitivity of NMR, which depend mainly on natural abundances. He emphasized on how the sensitivity could be increased. He vastly discussed about the dynamic nuclear polarization with many examples and applications. So, it was very enriching and very informative session. We sincerely look forward to such program in future too. Thank you, sir.
Thank you, ma'am, for your input. Thank you once again.
Thank you, madam. I now request Ms. Archana Mendonça to take over the second session. Thank you and have a pleasant day.
Thank you, Ms. Bindu Narona. An idea that is developed and put into action is more important than an idea that exists only as an idea. A pleasant afternoon to you all. I, Archana Mendonça, Assistant Professor, Department of Chemistry, will be the MC for the second session. Once again, I would like to welcome all the participants for this session. Dear participants, please note, if you have any questions during the presentation, just write them in the chat box, which will be discussed at the end of the session. We are honored to have with us Ms. Apurva, CEO, Startup Webinar Park, as a resource person for this session. I welcome you, ma'am. I request Dr. Nandini K, Assistant Professor, Department of Chemistry, St. PHILOMENA'S Postgraduate Studies and Research Center, to introduce the speaker.
Good morning, one and all. It is an honor for me to introduce our distinguished speaker, Ms. Apurva, International Trainer and CEO of Startup Webinar Park, for the second session. Madam got her Master's in Artificial Intelligence from Oxford University, UK. She was a research assistant at Nanyang Technological University, Singapore, and a software developer at Amazon. She has worked as a trainer in the field of artificial intelligence through interactive and engaging sessions, and has helped students and professionals from countries such as USA, UK, Malaysia, and Saudi Arabia to gain better understanding and hone their skills. The varied projects in machine learning and natural language processing has been undertaken by Ms. Apurva, and it adds to her credit. With this brief introduction, now I welcome her and I request her to take over the session. And the session will start with a small break. Thank you.
Hello.
Hello, ma'am.
Hi.
Yes. Is it audible?
Yes, you are. Am I audible to you?
Yes, ma'am. Yes, of course.
Okay, thank you.
Okay, ma'am. Ma'am, could you please share your PPT?
Yeah.
Okay.
Can you all see my screen?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay, perfect. Hi everyone. A very good afternoon. Thank you to the Department of Chemistry, St. Philomena's College, for having me today. So my focus in today's short session is to kind of give you an idea how LaTeX can be used in the field of chemistry. So my background is not in the field of chemistry, and just to prepare for this presentation today, I did some research yesterday, and that's the most I've been exposed to chemistry in the last 10 years. So bear with me if I get some of the terms wrong. Yeah. All right. So let's just get started. Okay, so LaTeX or LaTeX. So what is it, right? So LaTeX is a typesetting program. So what it does is it helps you to generate professional looking documents with like minimal effort on appearance. Okay, so LaTeX can be considered as a programming language in itself as such, because when you say typeset, what do you mean typesetting? Typesetting is nothing but uh, you have your content. You basically have to make your content look in such a way, right? Example, when you're writing a thesis, you have a front page, chapters, and as such. Whereas when you're writing a journal paper, you have like introduction, methodology, related work, so on and so forth. So, and each of these sections and content has its own like fonts, size, style, so on and so forth. So bringing all these appearances of the document together is called typesetting, right? So what LaTeX does is it uses a bunch of commands or instructions such that like you get a very good professional looking document. Okay, so to start off, so here you have a bunch of commands, right? Okay, you have something called as backslash document class, backslash begin, backslash end. Okay, so these are all LaTeX commands. Okay, these commands are returned in a file which has .tex extension, right? Like in Word, you have like the .docx, right? Docx extension. Similarly, the LaTeX file, I know it might feel a bit alien like this way of writing your documents, so just bear with me. So what you do is you don't start writing the document as such. What you write is a source code, which is a .tex file, which has your content as well as latex commands. Now latex commands always start with backslash command name and some input. Okay, we will go into each of these commands a bit later. Okay, but for now, just whenever you see a backslash something, it just means a latex command. Okay, and then I have my content here, hello world, blah blah blah. Okay, now this is my .tex file. Okay, now this .tex file must be understood by a machine and then generate the corresponding PDF file. So what it should do is your latex software will tell your machine what your commands are, right? And then it will later generate a corresponding PDF. Now, if you generate these 4-line command, 4-line program, .tex program in a uh, in in a text studio or any IDE, what you get is a generated PDF. So this alien looking file is now converted into this good looking document, which is like A4 size, 10 point font, and you also have a page number. Okay, and you have like a 10-point font size. Okay, and it is A4 paper. So all I did was write my content. Okay, what it gave me was a good aligned statement with also the page number. I didn't have to write anything extra. Okay, so the way this default typesetting is done is via the latex program in itself. Okay, so I have just copy pasted the zoomed in version of the text that was printed here. Now if you see this backslash latex, right, up in my code snippet was now generated as like this latex logo, right? So in latex, the commands in itself have result in a way the way contents are generated in your PDF. Okay, so this is quite different from what you would do in Word. In Word, you would basically type like what you would see in the PDF itself, right? Whereas in LaTeX, you use commands to kind of minimize your effort on appearance. Okay. Now, looking at this small document, it might feel like this is an overkill. Okay. But the end of this session, what I wanted to show you is this is not an overkill, especially when you write like large documents such as like your thesis, a book. Okay. And even for why it's a good option to use LaTeX for journal submission, conference submissions. Okay. Now, before we look more in depth into LaTeX, say you want to install LaTeX onto your system, right? So there are two things that you have to install. One is the LaTeX distribution in itself, okay? Because the LaTeX distribution is nothing but the LaTeX software, right? Which helps your machine to understand all these LaTeX commands, like for example, your document class, yeah, and your begin document, so on and so forth. So now the LaTeX distribution that you will be downloading will depend on the operating system that you are going to use. Okay, may it be Linux or like or other like Ubuntu, Pop OS, and you have Mac, and then you have Windows, right? Based on the type of OS, you will be downloading the LaTeX distribution. Okay, so without downloading these LaTeX distributions, your machine will not be able to process the .tex file. Now, this is optional, but I would say is necessary for especially beginners, which is the IDE, the Integrated Development Environment. So you can write the .tex files using Notepad. Okay. Now a Notepad will not give you any help. You're all alone while writing the .tex files. You wouldn't know if you have made any mistake in your commands, right? And you are kind of like left to fend for yourself, wherein like you have to remember all the commands, right? It can be a bit daunting. Okay, so in order to overcome that, you have to it will be a good plus to install a LaTeX IDE. There are many, all right, TextStudio, TextMaker, and Leaks. So this is just a snapshot of how an IDE looks like. Okay, so this is just a snapshot that I took of my TextStudio. Okay, so if you see, this is my .tex file, and this is the generated PDF file. So you have it side by side, right, such that, like, you can like have a good look of what's happening. And also, say you're going through your PDF, right, and you find there is some mistake here. Obviously you can't change your PDF, right? You can't edit a PDF here. So what you have to do is you have to jump to the corresponding location in the .tex file. With the IDE, this jump is automatic. So if you right click on this, the position in your PDF, it will automatically bring you here, which will be the corresponding position in your .tex, right? So you don't have to like skim through the whole .tex to find the place where you want to make a change. Okay, and you also get like this nice panel of symbols. So what this will do is this will automatically generate the code for these symbols as soon as you click in the .tex file. Okay, similarly it will give you like auto suggestions. It will also give you like some of the commonly used commands, right, so on and so forth. So this is why IDE like makes life easier. Okay, suppose you don't want to install anything on your system and you want to just start using LaTeX as is. What I would suggest, obviously there are a lot of online platforms, but you can give Overleaf a try. The reason is Overleaf also has, you know how you have W3 schools for like all this web design and HTML and all of it. Overleaf can be considered like equivalent to it. So Overleaf has good tutorials for you to start off, and you can open those snippets in the tutorials in your Overleaf editor, so on and so forth. So it's a good, in fact, I suggest beginners to just like use Overleaf if you find the installation a bit daunting, and it is free as well. Okay, now before we look into the features of LaTeX in more into detail, let me just compare like Word, which is the most commonly used, like document generation tool, with LaTeX, right? So Word is, I kind of covered this before, is a WYSIWYG. Okay, WYSIWYG implies what you see is what you get. Okay, so that implies when you're typing a document in Word, at any point you're looking at the final document, right? That means your final document does not change from what you're typing at that point, right? In LaTeX, as I explained before, you are typing a .tex file, right? So suppose you're using like some commands, like in our first file we use the \LaTeX command, right? So this is not how it will generate in the PDF, right? It will generate the LaTeX logo. So at the time of writing your LaTeX file, you are just typing what you mean. So what you see is what you mean, right? And once you click on run, it will render the generated PDF, and then you will see, okay, how it will look. The reason this is good is because when you're typing content, you will not be disturbed by how the appearance will be looking, right? Inadvertently, you can't have like your final document looking shabby, right? But like when you're writing .tex file where the content is separated from appearance, it comes naturally for you to concentrate on the content. Okay, yeah, LaTeX has a initial steep learning curve, which can be a bit off-putting for people who write like small documents. But say if you are writing like for theses, or like you're going to submit a conference or a journal, submit papers to a journal or conference, then it makes sense to invest some time to learn LaTeX, right? Especially, so LaTeX is widely used in the field of computer science, mathematics, physics, because you might have a lot of equations, figures, tables, references, right? And LaTeX organizes it very well. And also when you're writing like a big document, like a again a thesis or a book, you can separate your code or chapter wise content into separate files, folders, so you can take a modular approach, right? And also like LaTeX is cross platform. That means like if you have a .text file that's developed in Windows, you can still run it on a Linux or other operating system, right? And then if I'm an Ubuntu and if I don't have Word, and if I open the .x file in like say LibreOffice or something, then there is a good chance that the format will be all messed up. Yeah. And one other good thing about LaTeX is that it helps, and that's why it's more popular in the academic community, is that the journals and publishers can come up with their own templates, right, using LaTeX, wherein like you just download the template. And at the end of the session, I actually encourage like people who are interested to do this. So go to IEEE or any of your related journals, and you can download a LaTeX template. All they will do is they'll have some styling done already, and all you have to do is just type in your content, and the content is no longer tied to your appearance. Yeah. So obviously those are like good pluses, but I know some of you might not be convinced, right? So that's why we have the remaining time to help me convince you to try and give a LaTeX a try. Yeah. So in the Hello World program that we saw, we had the document class command, the begin document, and the end document command. Now, these three commands are the basic commands for a .text file. So, without these three commands, you do not have a working .text file. Yeah. So, the document class basically tells you what are you writing. Okay, is it an article, is it a book, okay, is it a report? So the reason it wants to know what you're writing is because LaTeX takes this minimalistic approach, meaning when you're writing an article, you'll have sections, right? Whereas when you're writing a book, you'll have chapters. Okay, so what happens is article has its own set of commands available, and a book will have a few more extra commands. For example, article might have only the command to create a section, whereas a book can have commands to create chapters, right? You also have the option to write letter, right? That time you have commands to generate to address, from address, signature, okay, so on and so forth. Okay, the begin document basically tells LaTeX, okay, this is where the content starts. So whatever you put between the begin and the end document, this part is called the body. Okay, this part is called the body. So whatever you put between the begin and the end will be generated in the rendered PDF. Okay. Now the part between the document class and the begin document is called the preamble. Okay, now whatever you put in the preamble is not generated. It is basically used for one of the few things. Okay, one thing would be you are seeing a command called use package. Okay, so this is also one of the pluses of LaTeX. LaTeX is open source. With open source comes a very big community when it is adopted widely. So you have a lot of people writing packages. Now, what is a package? Okay, I told you LaTeX comes with a set of default styling, and when you write your content, it will use those default styling. But what if you don't want this default styling? What if you want to make use of something different, right? Like for example, say you're writing a list. Okay, so usually a list is unordered list, or an ordered list has numberings, right? 1, 2, 3, 4. Now, I don't want this 1, 2, 3, 4, but instead of this, I want my list to incrementally generate step 1, step 2. Okay. So this is something customized, right? So when you have to do something, some customizations, you use a package. Okay. A package is nothing but a code written by someone else to achieve a set objective. Okay. So when you install LaTeX, it comes with the bare bone stylings, right? When you use package, okay, you can, there is something called as the LaTeX CTAN. So wherein you can check the available packages, okay, or when in doubt, just Google. There's always a package which someone will suggest in Stack Overflow. So what you have to do is you just have to write use package and package name. Okay, this is some whatever you see in square bracket are some temporary arguments taken by the package, all right? Okay. So now package is nothing but some code that others have written that you're using to achieve some objective. Okay. Now I have used input enc. The reason that I have used this because when I use, I don't want to confuse you because I don't know if you will know ASCII characters. So this will help me to use like non-traditional characters. Okay, in my file. All right. Now, use package. So, any external library that you want to use, you will write it here. Okay. Usually, if you're using Notepad, then you have to manually download and like let LaTeX know where this package is. But if you're using an IDE, okay, if you use a library which is not installed, it will automatically install it for you. Okay, so when in doubt, just Google and find the package name, and once you have the package, just use the \use package command and the package name. Okay, now having that out of the way, I just now want to like give a title to my document followed by the author name followed by the date, some content, and also want to give like this footnote, okay, which is connected to my name here. Okay, so the way I do this is by using this self-explanatory commands called \title, \author, \date. Now all I did was \title first document, right? \author Apurva. Okay, now this \thanks is actually what generates this footnote funded by Webinar Park team. Okay, and then you have a \date. Now, you remember I told you whatever you put in the preamble is not generated. But then you might question me, why is this generating? This whole generation happens because of this command called \make title. Okay, so make title has, what it does is it goes to the preamble, it picks up, okay, is there a title? Yes, there is. Is there an author? Yeah. Is there a date? Yes, it is. It just gathers all this information and typesets it as the way you're seeing here. Okay. So as you can see, I didn't do any styling, right? All I just gave the inputs are through commands, title, author, date, and a thanks. Whenever you write thanks, you can, what it does is it will automatically give the thanks, whatever input you give to the thanks in the footnote, and it will associate it with the name that you want to put next to. Obviously, you can have varied types, multiple names, names with designations, email, and all of it. And all you have to do is just use these 3 commands, okay, and just give multiple inputs, and that is it. You don't have to like format like what will be the size of first document, what will be the size of the relative sizes, okay, relative sizes of the author name and date. It's all taken care of, and it also nicely puts like whatever footnotes that you have to put, right, thanks to the \thanks command. Yeah. um that's pretty much here. Okay. Yeah, so I know there are a lot of commands to begin with, but then there are pretty self-explanatory, like title, author, date. So it's all about practicing. Yeah, so it kind of like is helpful because like if I were to do it in Word, then I would have to like think about what would be the relative sizing of each of these elements, right? But do note that I have given some temporary arguments in my document class. 12 point. This is just the font size for the entire document content. For example, for the main content. Okay. Letter paper, I told you by default it generates A4, but here I've given letter paper. You can give different values. Again, check Overleaf. Overleaf has amazing documentation onto what type of inputs you can give. And I've also given another input of being two-sided. Usually the documents that are generated are one-sided. So this will just say it's a two-sided document. Yeah. So now let's just quickly see what tables does. Okay, so again, this can be a bit daunting in the beginning, but then why I prefer tables in LaTeX, even though Word is easier for tables, is that okay? One amazing thing is automatic referencing. Okay, so I have a table. So this whole thing from the begin table to the end table is what defines a table. Okay, and this basically gives you what goes into the table. Okay, so obviously in Word you would just click on the number of rows, number of columns, and then, like, you would then populate the values. But what LaTeX uses is, in the when you define the content of the table, it basically asks you, I've written C. How many C's are there? 4, right? How many columns do I have? 4. Yeah. So now what is this C? Okay, C is nothing but center. Now if you see, uh, all the elements of column 1, 2, 3, of all the elements in all the columns are all centered, right? So you can use R as well, R or CC. So what it will do is, the first 2 columns will be right aligned and the next 2 will be center aligned, right? So what it does is, it clubs the number of columns with the alignment of the content in each of the columns, right? So what it does is, it kind of like uses symbols, or it uses just, like, alphabets to kind of like achieve what you would do using UI in Word, right? You would use click on right alignment, center alignment. Here you have to use the letters RCL. Okay, now, okay, you have defined the number of columns here. Okay, but then how do you define, okay, I have now finished putting the content in my first column. That is done using the ampersand. Okay, so column 1 ampersand. So ampersand indicates the end of that column content. Okay, and then you have column 2, and then you have an ampersand, right? So each ampersand indicates the end of the content for that column. Okay, okay, so now you are done putting for all the data into all the columns, right? Now you want to say you're done with this row, you want to move to the next row. How you do that is by the double backslash. Okay, so you have the ampersand, you have the double backslash. Ampersand indicates end of column, and double backslash indicates end of a row. Okay, so this is just an indication of how you would create tables. Okay, now why would I still prefer this way? Okay, the reason, because I can reference my tables easily. Okay, now what I do is, I give a name to the table. It's called table colon data. Now this table is automatically given a number, okay, by LaTeX. Now whenever I want to reference this table anywhere in the document, I just make use of the table name. My table name is table colon data. So if you see table backslash ref, now ref implies that you are trying to reference to an entity. And which entity are you referencing? You give the name of the entity. In my case, it is table colon data, right? So one thing is, you can also easily give captions using the backslash caption command. Okay, so all this gibberish looking code actually generates a nice looking table with a caption, right? And this table can be referenced anywhere in the document using the table name. The table name is given using the label command. Make sense? So similar, you have to do the similar thing for a figure. So again, you have the begin figure, end figure. Inside that your content goes. Here is where you will provide the name of the figure, and a figure gets a caption like a nice plot, and then it also has a label. Now a label is not generated. Okay, a label is just a name that you give internally for your figure. Okay, so now this whole snippet generates this, right? It generates the figure, and it also gives a number. The numbering is continuous. Okay, within the whole document by default. But for some reason you want to make the numbering section specific, that can also be done using appropriate packages. Okay, now I have the figure. The name of the figure is fig colon mesh 1. So as you can see here, if I want to reference it, I don't have to remember the figure name. The reason, because you keep writing the document, right? Now it's figure 3, right? So later on you add an image before this figure. Now this plot, a nice plot, will becomes figure 4. So dynamically the figure numbers can change, right? So you don't have to statically encode what the figure number should be. Okay, and also similarly you can reference the page in which the figure comes, like using the pageref command. So here the figure comes in page 7. So as you can see in the figure 3, the where you get the number 3 is from the backslash ref. Okay, so backslash ref is to reference an entity, may it be a table, equation, figures. Okay, and backslash label is something that you use to give a name to an entity. Okay, so I thought that it would be a good idea to look into chemical equations rather than mathematical equations, right? So to be honest, like obviously I have I have not written any documents that are remotely related to chemistry. So but these packages have been widely used, right? So it can look a bit daunting, but like it is pretty simple, as in when like you try to you understand the gist of it. Yeah, so the first package that we'll be discussing is that mhchem. Okay, so what this does is it basically gives typesetting, or like the appearance of how the chemical equations or the formula should look like. All right, so I have no idea what this equation does, but I did like pick it up from their documentation, right? So you have the command backslash ce, right? As I said, okay, mhchem is a package, right? So if you want these commands backslash ce to be available in your latex document, what you would do is you would first do use package. Use package mhchem, right? This is what you would do. Okay, so once you have this line, you then get the commands backslash c. Now if you don't tell latex from where you're picking up backslash c, you will get errors. Like, yeah, without this statement, all this will be errors, right? So anyways, so as you can see, I just backslash c, and whatever goes into the curly brackets will be your um will be your like your actual like required parameters. Okay, required input rather. So I'm giving the input CO2 plus C, and this is just normal arrow, that's the slash and then the angular bracket, the hyphen and then the angular bracket, and 2CO, and this is how it's generated. So whatever number that you put before the atom like C, right, it generates into a quantity, right? And whatever number that you put after the O, it gets generated into a subscript like this, right? So similarly, if you want to put anything in a superscript, you will use this cap. Yeah, and if you want to get a vertical downward line, you would use the letter V, right? So in latex you have the meanings associated with different symbols and with different letters, individual letters, right? So you should be careful like what you use where, right? So, and also make sure that these symbols and letters have a specific meaning only within this angular brackets, right? Because someone would have written the command, the program for what this backslash ce does, right? So they would have defined these special functionalities to these symbols or characters. Okay, so if I were to write CO2 outside this backslash CE, then my rendering will not be the CO2 that is defined by the MHChem. It will just display as CO2 as is. So if I want a nice CO2 like this, like with the proper subscript and all of it, then I have to use the backslash CE and inside the curly brackets. Okay. I have read that in Word you do use Chem for Word or some kind of open source software to kind of define like this molecular structures, right? So in LaTeX, the corresponding package is ChemFig. I strongly recommend you to take a look at the Olive ChemFig to get more idea about it. Yeah. So now, MChem you would use just to write down like typesetting for all this chemical formula and equations. But ChemFig, as the name suggests, is for mostly drawing the molecular structures. Okay, so you have different ways to write the bonds. For example, if you write backslash ChemFig, okay, O equals H. Okay, this will be rendered as this O double bond H, right? So there are different types of bonds available, and obviously I don't know the names of all of them. I know they are available. Okay, so do look up the documentation of ChemFig in OLEAF. Yeah. Again, it is also possible to write like different structures like this pentagon, hexagon structures. So the structure is pretty straightforward, like at least for me coming from a non-chem background. So it's like backslash chemfig, and what I do is I write my starting atom name, which is A. Okay, star 5 implies it's a pentagon which starts with A. Okay, and then I start with a single bond from A, right? And then my next atom will be B, right? And then it will be a single bond from B to C. Yeah, single bond from B to C, right? The bond is defined by the hyphens or equals, right? And the atom name is written by the atom name in itself, like B, C, D, whatever it might be. And what you do is you start, A is your starting atom, and relative to that you start filling it up, right? You start from A, and if there is going to be it's going to be a pentagon. So you A to B, the bond is defined by the first, whatever, it's a hyphen here, so it's going to be a single bond, and then the next atom B, and then the next bond C, and so on and so forth. Now suppose if you don't write the atom names, you get like a closed bond kind of thing, like you don't have the atom names, all the lines are joined, right? And it is also possible to create incomplete rings. Say you write 6 but you don't give like 6 bonds, right? So it becomes like an incomplete ring. Okay, so what it does is your starting atom or the point will be this. Okay, relative to this, you start filling up the bonds with whatever you give within the curly brackets. So the equals will give double bond. Okay, so you are now here, and then you have a single bond, so you are now here, and then you have a double bond again, and then a single bond, a double bond, and a single bond. Okay, I would say give it a try. I had fun with it. Yeah, so but yeah, just give it a try and see like how it works for you. And obviously, like, I'm not going to trace this out, but do it as a homework and just see if you can figure it out. Yeah, it is pretty simple. The star 6 basically tells you how many what is it going to be, a pentagon, hexagon, right? Yeah, so it is possible to write complex molecules, right? And anything that you do in a flexible manner, right, helps you to customize better. Okay, similarly, because you are putting in I think in chem for word it will automatically generate, right? But here obviously you do have to like specify. Okay, like what are all the bonds, the bond types. But with doing so, the advantage is that you can customize how your molecular structure looks, meaning you can add different colors. You can also like change the space between the atoms, like in the when it's rendered, if you see the space between the atoms is more like, is less here as compared to our previous diagrams. And you can also associate a name to the figure that you have generated. So all this will be like one entity, right? You can also generate like Lewis structures. Please don't ask me to explain this, what a Lewis structure is. I can explain the code for you. So again, you use a package called Lewis, right? So you have like use package, and it's called Lewis. Okay, and this package gives you the command \Lewis, right? And what it does, okay, \Lewis is followed by 9 pairs of curly brackets. Okay, the first pair is the atom name, right, which is X here, followed by the positions around the atom. Okay, so the first, after you write the name, the first curly bracket generates here. The reason I'm showing you these positions is here. Later on, when you want to put dots around it, you can know where to put it, right? If you want it in position 1, put it in the first bracket after the name, right? If you want it in position 3, put it in the third bracket after the name. But this is how it will be rendered. Now, if you look at this command, okay, you have your F, right? Surrounding F, you have the dots in the first 4 brackets, right? So this is 1, 2, 3, 4. 5 and 6 are empty, so there are no dots. Okay, and 7 and 8 have dots, so this is 7 and 8, right? So the first picture is to just show you which the position for each parenthesis. Okay, so if you put up a dot, in which position will it be generated? So once you know the position, you can put your dots as and along how you want to render it. You can also generate electron rings using like one commands, using this package called board. So you have like the helium and nitrogen. Okay, and then here you say you want to have 2 electrons and it will like generate it, and here you want to say you have 7 electrons and it will generate in the electron rings. Yeah, so these are a bunch of things. I know there are a lot of commands, right? But then it's all a matter of practice. So you can generate it quickly, and it's open source, and there is a lot of options to customize. Okay, so coming back from the chemistry thing to the generic thing of reference management, right? So you have how do you manage references in how does LaTeX take references? Okay, now this might be super off-putting, but don't worry, you don't have to write all of this, right? You so the way LaTeX takes references is through these kind of like records. Okay, so what each of these record tells is, first one tells you whether it's an article in proceedings, and so on and so forth, and then it gives you a name, okay, for each of the papers. Okay, and then followed by the author, title, year. Okay, you can have more than these as well, but the minimum is the author, title, year, and the probably the publication. Okay, so you don't have to generate all of this. You will be using, as if you are into research, you will be using a reference manager, right? Either Mendeley, okay, or Jabref, anything that is that you're comfortable with. So whenever you come across a research paper that you will be using or you are interested in, you would put it in your reference manager. Okay, your reference manager, almost all of them have an option to generate .bib file. You remember the .tex file that we used for writing LaTeX code? The bibliography is actually stored in a separate file called .bib. Okay, so whatever papers that you have put in a reference manager, when you ask it to generate a .bib file, this file is automatically generated for you. So you don't have to worry about it, right? So what you have to do is, whenever you put a paper into your research manager, that paper is automatically given a key. That is the key that you see here. Apurva 2020 research, 10 2008 vulnerability, right? So on and so forth. These names, whenever you want to cite these papers, you will be using these names. Okay, so these names also you don't have to come up with. Usually the reference manager comes up with it. And also you can look into Google Scholar as well. If you look into any Google Scholar paper and if you want to cite it, there is an option to get the bib entry, or the entry looks like these records which already has the key, author, journal, everything. All you have to do is you can just paste the bib entry directly into your reference manager. Reference manager will parse it and it will show you into human readable structure, meaning it will give you in a nice array and all, not in like these records. Yeah, but internally this is how it is saved, right? So usually for bibliography, to generate a .bib file, till now I have not done it manually, and I don't recommend it doing manually. It's also always use some kind of a good reference manager. Okay, now if you have once you have the references and the .bib generated, your IDE will give automatically give you suggestions. Okay, whenever you use the .cite command, okay, your ID will automatically give you the recommendations for all the papers that you can cite. Okay, so once you put like cite, say some paper name, right, and when you render it, this is how it's rendered. Okay, you are given a number 3 to whatever. Now where does this number come from? The number comes from this references section. Now mind you, this references section you don't have to write. Whenever you cite a paper, by default, whenever you cite, automatically that paper is added to the references section. Say you have 100 records in your bib file, right, but you have cited only 10, then your references section will only have 10 papers, right? That should be the norm. You should never include papers that you have not cited in your references section. Okay, that's not ethical, right? So whenever you cite a paper, it is automatically added to references section. So it's a breeze. You're actually not maintaining the references section at all. Even like, this whole part, like 1 2 3, the way it's rendered, right? There are different styles, like, IEEE style, the ACM style. Yeah, so based on the journal that you're writing for, they would have automatically used the package and encoded the style that they will need for their paper, right? So you don't have to worry anything about references. I would strongly suggest to kind of like either look into learn LaTeX in 30 minutes in OLEAF, or just download a LaTeX template from one of the publications and just try filling in some data and understanding how it will work. Yeah. So this is basically the references that I've used, and that's pretty much it for this session. So let me know if you have any questions.
Thank you, madam, for your words of wisdom. Now I request Dr. Asha MS to take over the question and answer session.
Thank you, madam. We have got a question from the participant. Is this software is useful to format references? Already madam has given details regarding this. Madam, I request if you want to add a few more points regarding the reference formatting, you can, madam.
Yeah, so references actually more than LaTeX, it depends on the good reference manager that you use. As I said, whenever you look up papers for your while researching, or like for even like writing your thesis and all of it, so always build a database of the papers that you'll be looking up in your reference manager, right? And once you have the reference, all the papers set and ready, you can automatically generate it into .bib file. Okay, and as I said, there are varied ways to format, like how your references section can look. Either it's an IEEE format or the ACM format. And if you want to use any other format apart from the established ones, it's also possible using packages.
Thank you, madam. Thank you for your additional information to the question.
Thank you.
Thank you, Dr. Asha MS. Now I request Dr. Nandini K to give an overview of the session.
It gives me an immense pleasure to conclude this session on LaTeX presented by Ms. Apurva. So she revealed us that LaTeX is a typesetting program help us generating document, and it comprises of bunches of commands. So most of us, including me, had thought that this LaTeX is a time kill, but with her presentation, I think she has changed our view on LaTeX. And she has clearly differentiated MS Office from, that is MS Word from LaTeX. And she has taught us how we can draw a table using LaTeX and insert an image, chemical equation, different chemical structures, starting from Lewis structure to the complex structures, and also how to add references to our document. So, madam, we will be looking forward for hands-on session in future about LaTeX. Thank you for your presentation. Thank you.
Thank you so much. That was a beautiful summary. Thank you.